So let us start this session. I am Tanmay Sharma, a Prime Minister's Research Fellow from Mechanical Engineering Department of IIT Patna, and I welcome you all to the seventh session of IC engines and gas turbines, where we'll discuss about the carburation problems and the methods which are used to increase the efficiency or the effectivity or the productivity of carburetors. So first, I would like to help you recollect what is the basic principle of carburetor and what is carburation. So carburation is the process of uh, air fuel mixture in an SI engine outside the engine cylinder. So you will see that. So as the this air fuel mixture is required into the cylinders, piston engine cylinders, and to the end of this part, there will be a piston engine cylinder, and there you will have to give a charge, and due to the ignition caused by the spark plug, the combustion will happen, and accordingly, the whole process will continue in a spark ignition engine, and that we know till now. And that mixture, the fuel air mixture, is prepared by these carburetors at a precise amount which is required by the engine, and that process of preparing the perfect amount of air fuel mixture is called as the carburation. And the carburetor is basically the device which prepares this air fuel mixture, and on the process of preparing it, it basically uh, prepares a homogeneous mixture. It atomizes the liquid fuel into vapor, and it homogeneously mixes with the air which is passing in to the carburetor, and accordingly it passes the air fuel mixture into the engine cylinder. So a carburetor, a simple carburetor, has the following components. This is the float chamber, and why it is called the float chamber? Because it has a float which is submerged in the level of oil out here, and has a needle bulb which actually, if the oil content decreases beyond a certain point, then this float will come down, and this needle bulb will come down, and the orifice will become open, and the fuel from the pump will be pumped inside the flow chamber, and accordingly this chamber will supply the fuel into this throat of a venturi, and that through a nozzle. So the nozzle or the metering orifice discharges the jet of fuel into the venturi, and the process of doing so, the liquid fuel actually oozes out from very small pores, and accordingly it automatically atomizes. The small droplets of fuel automatically atomizes due to the heat of the inlet air, and a uniform mixture is formed. So that is the nozzle with the metering orifice. The venturi is provided in order to cause a pressure difference. So we know that as the air is coming inside, there is a pressure difference due to the suction at the piston engine cylinder, and as the air comes due to the suction, as it moves through the venturi or the throat, what happens is that the area decreases. As the area decreases, the velocity increases and the pressure decreases due to Bernoulli's theorem. And here the pressure is high. As a result, venturi depression is produced, which actually causes the flow of this fuel from the into this venturi. So the we'll see that the pressure at which the float operates is the atmospheric pressure, because it is open to the ambient through certain pores. It is connected to the ambient. Here also it is connected to the ambient, and the pressure here is less. So there is a pressure gradient due to the decrease in the pressure of in the venturi, and accordingly the fuel comes out into the throat. Then we have a throttle valve, which actually controls what amount of fuel air mixture should pass into the engine cylinder finally. So that is the purpose of the throttle valve. Now there are a few points. The fuel level is slightly below the outlet of the jet when the carburetor is inoperative. Yes. So actually there is if the carburetor is not operative, then we want that no oil should leak out, right? So if the level of the oil in here is higher than the level in here, there will be a pressure gradient which actually pressurizes the fuel into this venturi or throat, and accordingly the oil will leak out when it is not operative. So that we do not want. Accordingly, there is a distance. The nozzle is kept a little bit lower than the this level of the uh, oil level in the float chamber. Then, sorry, the fuel level is slightly below than this nozzle out here. So the you will see that the fuel is this is at the height and this is at the height. It will not come up. The nozzle jet has a fine bore. Yes, the nozzle jet out here has a very fine bore, and through the bore the oil oozes out. The oil issuing from the jet is in the form of fine spray. Oil issuing from the jet is in the form of fine spray, and it vaporizes quickly and mixes with the air. As a result, the air-fuel mixture enters the engine cylinder and is controlled by the position of the throttle valve that we know from here. Next, let us talk about different conditions in which the engine runs and accordingly how the carburetor should supply the air-fuel mixture. So, if we see the air-fuel ratio, this is increasing in the downward direction. So, rather, if you see that the fuel-air ratio will be increasing in the upward direction. So the different conditions is that first is the idle system when the vehicle is at rest. It suppose in a case of speed breakers, the lows we'll have to operate at low speed. Then in case of traffic points, the car is at has to be stopped. Then idle system should be applied, and here the air fuel ratio is quite low, or the fuel oil ratio is quite high. So you see more amount of fuel should be supplied in this kind of systems, and that's a contradicting statement because the engine is at rest, means engine is starting but it is at the lowest position, but still we'll have to lowest RPM, but still we'll have to supply huge fuel. So the reason behind this is that when this is a engine and carburetor system. So when idling is happening or low speed conditions are happening, then what happens is that the pressure difference at the cylinder, which is caused due to the burning of the fuel and the ambient, is not sufficient to make the whole of the burnt gases leave through the exhaust valve. So the pressure difference actually, when the piston is coming back to the top dead center, it basically uh, uh, pushes the burnt gases through this exhaust valve into the outside, and a huge pressure would actually mean that the entire of the combusted gases can leave through the exhaust valve. But that is not the case at low speed conditions because the RPM, or the revolution per minute, is quite less, and the pressure difference is not sufficient to make all of the this burnt gases to leave. And accordingly, what happens is that in the suction stroke, some amount of gases will still remain at the top part of this piston, and accordingly, when the new charge is added, it will mix with the burnt gases, and it will reduce the means it will reduce the first of all the amount of fuel which needs to be burned, and it will dilute the entire system. So this is called as the dilution. In order to avoid that, a larger amount of fuel is passed, and so that the combustion pressure actually is up to the mark. Accordingly, a higher fuel air ratio is supplied, or yeah, so 1 to 11 or 1 to 1 is to 12. So that is the reason why in the idle system a higher fuel air ratio is required. Then there is the main metering system, or when the car is moving in normal power or cruising. So that is the 25% to 75% of rated power. And main metering system it has the objective of supplying the fuel at economy. So the fuel air ratio is a little less than the stoichiometric ratio. So you will see that. So this is actually air fuel ratio. So air fuel ratio will be 16.5 air and 1% of fuel. So it is a little bit below the stoichiometric. And why below? Because what happens is that complete combustion does not happen inside the cylinder due to non-homogeneous air fuel mixture. So the carburetor sometimes at these load conditions, it is not able to completely make a homogeneous mixture of fuel and air. And in that condition, since air is not available for in homogeneous condition, the combustion may not be complete. Some amount of the air fuel mixture will remain unburnt, the fuel will remain unburnt, and accordingly that's a big loss. In order to completely combust, we need extra amount of air, and that extra amount of air is supplied, which actually reduces the air fuel ratio below the increases the air fuel ratio below above the stoichiometric ratio. So that is the case of the main metering system. And then we have the maximum power system, where the power system and the uh, it is applicable for loads from 75% to 100% of rated power. So a rich fuel mixture is supplied like 13 is to 1. So 13 is the air and 1% is fuel. And why it is required? Obvious, that is obvious, because more amount of fuel indicates higher combustion pressure and higher energy, and that energy is transmitted into increasing the speed or the torque of the engine, and that is required. That's why. Also, there is one more reason, that what happens is that at higher load operating loads, at higher operating loads, the engine will have higher temperature throughout, because of the higher energy dissipation, and um, higher combustion is occurring. So the energy dissipation will be high. Accordingly, the temperature of the exhaust valve will be quite high. And in order to reduce the temperature, because we do not want the exhaust valve to melt down, so we need to reduce the temperature of the exhaust valve. In order to do that, we need to the extra fuel is supplied such that the fuel does not burn and the fuel leaves in the liquid state and gets in touch with the exhaust valve. And since the fuel is in liquid state and it has a particular specific heat capacity, the specific heat capacity will actually take away the thermal mass of the liquid fuel will take away the heat uh, of the exhaust valve, and it will maintain the exhaust valve at a particular temperature. So that is the case. And higher fuel content is also responsible to cool down the flame and exhaust manifold. All of the fuel is not burned due to insufficient air. Unburned fuel absorbs the heat produced in the flame as specified heat. Yes. So here what happens, the full air is not burned, and sometimes we want the combustion to take place controlled way. So we do not want the heat to be dissipated too much to the exteriors. So in that case, the unburnt fuel, it has a particular thermal mass that takes away the heat, some amount of heat, and it is ejected out through the exhaust valve. In that way, it takes away the heat which is not necessary through the exhaust valve, and our system remains in stable temperature conditions. So that is the case. That is the detail about the mixture requirements required from a carburetor. And in order to have these different conditions of mixture requirements, a simple carburetor will not suffice, and we will see why. And accordingly, there are some adjustments made to the carburetor, such as we have the idle system, then transfer idle and main metering system, then power system and main metering system. These things are added to the carburetor, or augmented to the carburetor, to speak, and in that way it actually meets the demand that is required by the engine cylinder. Next, we have discussed in the previous lecture itself about the carburetor theory, and through the carburetor theory we have discussed that the main purpose of having a particular theory for the carburetor is to estimate what is the air fuel ratio, or the mass of air divided by the mass of fuel. So we need require that, and for that we need to estimate what is the mass of air passing through the carburetor through here, and what is the mass of fuel. And The reason behind the passage of any fuel or air is the pressure difference that is created. So the pressure at here is lesser than the pressure out here, also the pressure out here. Accordingly, the fuel and the air passes through the venturi throat, and that's where we need to calculate the mass of air and mass of fuel. For calculating the mass of air and mass of fuel, we can apply two types of methods. One is the exact analysis and one is the approximate analysis. So in the approximate analysis, generally it is considered that the air is incompressible, right? The air is incompressible, which is not the case in kind of heated systems. And through that, they have developed the theory that the mass of air to fuel will be uh, dependent about the following things. That is the pressure difference out here, delta PA, and the G JAD rho F. So this is the manometric pressure head, which is faced by the fuel out here. So generally what happens is that the oil pressure is a little bit down. It is not at the tip due to oil level, because it is maintained in such a way, because in when the carburetor is not in operation, the oils do not leak out, and that's why the particular JAD is, that is the dip is created. And in order to overcome this manometric pressure head also, we'll have to supply the we'll have to compensate from the this pressure head that is generated. That's why delta PM minus G jet rho F. And that is also dependent upon the area of the throat. So, and the area of the fuel nozzle. Also, the venturimeter this constants. So, discharge constants of various things like the this of the venturi and the discharge nozzle. So, the approximate analysis tells that the mass of air to fuel is dependent upon these variables. And if we are having these particular values, then we can directly calculate what is the air fuel ratio. And in the exact analysis, in contrary to approximate analysis, it actually considers the air to be compressible. And that is the actual scenario. And that's why it is called as the exact analysis. In that, uh, for calculating the mass of air, they have used uh, this SFE equations, steady flow energy equations, to calculate the mass of air. And in approximate analysis, a simple Bernoulli's theorem, okay, is sufficient to calculate the mass of air. So in exact analysis, if somehow we are given the inlet conditions, the temperature conditions inside the carburetor, then it is actually advisable to actually have the exact analysis, because by then we can exactly calculate what is the air to air fuel ratio. And this is the formula. It is dependent upon the pressure at the throat divided by pressure to the one, that is the ambient pressure, and also other parameters which is seen over here in the approximate analysis as well. So this was the carburetor theory, and we will continue with solving a few more problems. And later we will, at the end of the uh, session, we will learn about what is this is only the simple carburetor. What are the different mechanisms which are augmented to a simple carburetor to increase the productivity of the carburetor? We'll look at that next. So right now we'll solve problems of the carburetors, and this is one of the this is the first problem. So let me read out. A simple carburetor under a certain condition delivers 5.45 kg per hour of petrol within an air fuel ratio of 15. Okay, air fuel ratio is given 15, and fuel the conditions of the fuel passed is given. The fuel jet area is 2 millimeter square with a coefficient of discharge of 0.75. Okay, if the tip of the fuel jet is 0.635 centimeter above the level of petrol in the float chamber, and the venturi throat efficiency of discharge is assumed to be 80%, then we need to calculate one, the venturi depression in centimeter of water necessary to cause the air and fuel flow at desired rate. Two, the venturi throat diameter, and uh, three, the velocity of air across the venturi throat. So we may take the density of air to be 1.29 kg per meter cube, and the specific gravity of the period is 0.72. Okay, so let us take a moment to get understand this question. So I will give you 1 minute to understand this question properly, and after that we will start solving the question. Okay, so let us solve the question. So these are the values which were given to us. We need to calculate the venturi depression in centimeter of water. So for the venturi or depression, first we need to calculate what is the mass flow rate of fuel. So we are given no actually we are given the mass flow rate of fuel, that is 5.45 kg per hour. Okay, and we do not know the venturi depression delta PA. We know the manometric pressure head G z rho f, and we know the area, we know the coefficient of discharge, we know everything instead of delta PA. So from here we can directly evaluate by putting the values of delta. We can evaluate for delta PA, and finally we will get delta PA to be 707.37 and Newton per meter, 752.22 Newton per meter square, and we will have to divide it by the um, this mass of the mass of a- the the specific gravity. For the specific gravity we have to divide it by 9810, and we will get this much meter of water, that is 7.67 centimeter of H2O, right? So this is our answer, the first answer. And for the second part, the venturi throat diameter, so we will first have to calculate the airflow rate, that is um, so the airflow ratio is given as 15, and we know the mass flow rate of fuel, so multiplied by 15 we will get the airflow rate. Accordingly, the mass flow rate of air equals to the we know this particular formula. Since the temperature is not given, we will use the approximate analysis, and we do not need the temperature out here. And finally, we will solve for the area of the throat, because everything else is known right now, and uh, we will substitute the area of throat with pi by 4 dt square. So dt is the diameter of the throat, and for we will solve for the dt value, and we will get the dt to be 2.86 centimeter. So that is the throat diameter. Next, we'll calculate the velocity of air across the venturi throat, ct. So ct or c2, so that is given as 2 g z rho f divided by rho a, and the value is given as 8.34 meter per second if you calculate, if you put on all the values. So this is the next question which came in the entrance exam of Bombay University. So a carburetor tested in laboratory has its float chamber vented to atmosphere. Okay, the main metering system is adjusted to give an airflow ratio of 15:1 at the sea level conditions. The pressure at the venturi throat is zero point 0.8 bar. The atmospheric pressure is 1 bar. The same carburetor is tested again when an air cleaner is fitted at the inlet to the carburetor. The pressure drop to air cleaner is found to be 30 mm of Hg when airflow at the sea level condition is 240 kg per hour. Okay, assuming zero tip and constant coefficient of flow, we need to calculate the throat pressure when the air cleaner is fitted and airflow ratio when the air cleaner is fitted. So let us take a minute to understand this question, and after that we'll try to solve it. Okay, so we now know that the flow chamber is vented to the atmosphere. So the flow chamber, the pressure at the flow chamber is the atmospheric pressure. Main metric system is adjusted to given, we know the airflow ratio, airflow ratio is 15:1. The pressure at the venturi throat is zero point 0.8 bar. That is, we know pressure which is reduced from atmosphere to that is zero point 0.8 bar. The atmospheric pressure is 1 bar. The same carburetor is tested again when an air cleaner is fitted at the inlet to the carburetor. Okay, so that is obviously it will produce give some restriction to the flow of the air, and there will be a pressure drop, right? The pressure drop to the air cleaner is found to be 30 mm Hg when the airflow at the sea level condition is 240 kg per hour. Okay, assuming zero tip at the constant flow rate, calculate the throat pressure and the airflow ratio when the air cleaner is fitted. So for that condition, we are given these values. We need to calculate the throat pressure when the air cleaner is fitted. So the quantity of air, the mass of air that is flowing is same in both the cases. That is correct. And for that, we'll simply use this particular formula, which comes from the Bernoulli's equation. We can get the exact mass flow rate, and we know all the values. Uh, do we know the yeah, we know all the values. So delta PA out here is 0.2 bar. Okay, and so this is when the air cleaner is not fitted. So in that case, delta PA is 0.2 bar. Now this pressure will be changed because the mass of air will be same, but the pressure will be changed. And let's assume that the PT is the throat pressure then. Okay, then we can use this formula, like delta PA dash is 1 minus this manometric head into 30 mm of Hg and minus PT bar. By using this formula, we will get uh, the for the same airflow and the constant coefficients, we have delta PA equals to delta PA dash. So yes, and in that case, we need to find, we'll just substitute the values and we'll find PT equals to 0.76 bar. So that was the case. Now we need to calculate the airflow ratio when the air cleaner is fitted. In that case, We now know that the delta PF equals to delta PA equals to zero point 0.2 bar. Okay, when the air cleaner is fitted with flow chamber still vented to the atmosphere, delta PF is 1 minus 0.76, that is 0.24 bar. As delta PF has increased, more fuel will flow, making the mixture richer, right? The new airfoil ratio equals to the airfoil ratio when the air cleaner is not fitted into root over delta PF without air cleaner divided by delta PT with air cleaner. And we will substitute the values and we will get the new airfoil ratio will be 13.69. So that's the answer. So next we go to the next problem, that is a simple jet carburetor is required to supply 4.6 kg of air per minute. The pressure and temperature of air are 1.013 bar and 25 degrees Celsius respectively. Okay, now the temperature and the pressure conditions are given. So I assume that we will have to use the exact analysis. So we will see if it is that if that is needed. Assume flow to be isentropic and compressible. Okay, so if isentropic and compressible is given, then we'll definitely have to use the exact analysis. And the velocity coefficient as zero point 0.8, we need to calculate the throat diameter of the choke of for air flow velocity of 80 meter per second. So air flow velocity is given at the choke. So let us take a minute to understand this question and we will try to solve it next. Let us try to solve the question. So we are given the following values: the mass flow rate of air, the initial pressure, the initial temperature, the coefficient of discharge uh, is given to be 0.8. The final velocity is 80 meter per second, and we have to assume the initial velocity to be 0 because it is comparatively very low. That's why we assume it to be 0. Next, this is the diagram, and we need to calculate the throat diameter of the choke of air, right? So the throat diameter D2 is, we will have to apply the steady flow energy equations at section 1 and 2, and we will have the following equation. H1 equals to H1 plus C1 square by 2 plus Q equals to H2 plus C2 square by 2 plus W. We know that the Q and the W are 0. So, and the C1 is 0. So the equation gets reduced to H1 equals to H2 plus C2 square by 2. Why Q and W are 0? So there is no work output from here, and we know that the flow is isentropic. Isentropic means there is no energy transfer through the system's boundary. That's why the Q is 0. Then we will solve for C2, is the velocity at point 2, 2h1 equals to root over 2h1 minus h2, and h is the enthalpy, and we can directly convert it to Cp into T. Cp is the specific heat at constant pressure, and if we substitute and we know the value of T1, for T2 we'll have to we'll have to get in the form of T2 by T1, where T2 by T1 we can actually, we know the flow to be isentropic, we can use the thermodynamic relationships to convert it into pressures, and that is being done here. So T2 by T1 equals to P2 by P1 whole to the power gamma minus 1 by gamma, right? And C2 actual equals to CV into root over 2 CPT1 into 1 minus P2 by P1 gamma minus 1 by gamma. So where Cp is given as R gamma divided by gamma minus 1, and we will get the value to be 1.005. We can directly use that for air. We can assume that also. Anyways, we will now solve for P2 because that is the only thing unknown out here. And finally, we will get the value of P2 to be 0.955 bar. So you see the calculation out here. If you do the calculations correctly, then you will get the throat pressure to be 0.955 bar P2. And accordingly, rho 1. So we need to calculate the throat diameter of the choke, right? So for that, we will have to consider the density conditions. So rho 1, we will get 1.1844 kg per meter cube. Then PV to the power gamma equals to constant. So P divided by rho to the power gamma equals to constant, and P1 by rho 1 to the power gamma equals to P2 by rho 2 to the power gamma, and then rho 2 equals to rho 1 into P2 by P1 whole to the power 1 minus gamma equals to 1.1356 kg per meter cube, rho 2. So we know mass flow rate of air equals to rho 2 A2 C2, and that is also equal to rho 1 C1 rho 1 A1 C1. That is continuity, mass continuity equation. We applied it in this case, and we have only one unknown, that is the throat diameter out here, A2, and accordingly we will find that the value of A2 is 8.443 into 10 to the power minus 4 meter square, or if we substitute, if we find the try to find the value of the diameter, so then D2 will be equal to 0.0328 meter. So that's the case out here. So 3.28 centimeter, right? So we have found finally the value of the throat diameter of the choke for air flow velocity of 80 meter per second. Now let us move to the next question, which has came in AMIE S 2001 from Nagpur University. So the question says, a simple jet carburetor is required to supply 6 kg of air per minute and 0.45 kg of fuel of density 740 kg per meter cube. The air is initially at 1.013 bar and 27 degrees Celsius. Okay, so the temperature is given. Then calculate the throat diameter of the choke for a flow velocity of 92 meter per second. The velocity coefficient is 0.8. If the pressure drop across the fuel metering orifice is 0.75 of that of the choke, we need to calculate the orifice diameter, assuming the CD, that is the coefficient of discharge, to be 0.6. So let us try to understand the question. I will give you 1 minute, and after that we will try to solve it. Okay, let us try to solve the question. So we are given the mass flow rate of air 0.1 kg per second, mass flow rate of fuel, that is 0.0075 kg per second. Then the temperature at the inlet is 300 Kelvin. Velocity at the throat is 92 meter per second. That's for air. Then discharge is 0.8 for air, and for fuel it is 0.6. Then the rho F, the density of fuel is 740 kg per meter cube, and the pressure at the inlet is 1.1013. Using these values, we will have to first calculate the throat diameter d2, the velocity of air at the ventured throat. That is given by C2 equals to CdA into this formula, which I actually have shown the derivation in the previous problem. You can refer back always. And here we actually need to find the value of P2, right? So the value of P2 is not given, P1 is given, and we'll have to find the value of P2. If you put in the values correctly, then you will find P2 equals to 0.937 bar. So that is the pressure at the throat. Okay. Then we use the thermodynamic relationship for isentropic process. The P1 V1 to the power gamma equals to P2 V2 to the power gamma, and the V2 is equal to V1 into P1 by P2 to the power 1 by gamma. Accordingly, we will get the value of V2 to be 0.898 meter cube per kg. Now, the mass flow rate is A2C2 divided by V2. The throat area is A2 equals to MA V2 divided by C2. So, we will get the throat area to be 9.76 centimeter square. So, we need the throat diameter. So, we will solve for the diameter part. Then, we will find the value of D2 because A2 equals to pi by 4 D2 square. And we will find the value of diameter D2 to be 3.525 centimeter. Okay, that's good. Now, we need to calculate the orifice diameter df, right? So the pressure drop, first the pressure drop, we now know the value of P2. So pressure drop at the venture is 0.076 bar, and the pressure drop at jet is 0.75 times of 0.076 bar. So it is already given that the pressure drop across the fuel metering orifice is 0.75 times that of the choke. So we now know that. So now the mass flow rate of fuel can be calculated as AF CDF into root over 2 rho F delta P, and accordingly you will get the area of the fuel orifice is 4.304 millimeter square. Also, AF equals to pi by 4 df square equals to 4.304. We will solve for the diameter of the orifice. So diameter of the orifice is 2.34 millimeter. So next, we directly go to the next question, that is for a petrol 4-stroke petrol engine of Hindustan Ambassador, we are given the following data. So we are given the capacity of the petrol engine, then speed at which the maximum power is developed, volumetric efficiency at the above speed, the air-fuel ratio is given, the theoretical airspeed at the choke at peak power, the coefficient of discharge of Venturi, the coefficient of discharge of the main petrol jet. So for the Venturi, that is CDA for the air, and for the main petrol jet, that is CDF for the fuel. Then the specific gravity of petrol, okay, level of petrol surface below the choke, so the JAD, which actually causes the manometric pressure head, that is given. Then atmospheric pressure and temperature, it is given at the inlet, so 1 bar and 20 degrees Celsius respectively. Then an allowance should be made for the emulsion tube, the diameter of which can be taken as 40% of the choke diameter. And we need to calculate the sizes of a suitable choke and the main jet. Okay, Then again, let us take 1 minute to understand this question and try to solve it. And after 1 minute, I will solve it. Okay, then let us try to solve the problem. So these are the values which we are given, and we need to solve the problem from here. So the volume of air induced is the volumetric efficiency into the stroke volume. So the stroke volume is Vs, and from that we can calculate what is the volume of air induced, that is into the cylinder, and that will also have to be passed from the carburetor, right? So that is the mass, the only the volume flow rate of air. So that is 0.03909 meter cube per second. Then the mass of air, mass flow of air, Ma equals to P1 V by RT1, and that is equal to 1 into 10 to the power 5 into 0.03909 divided by the value of R and the temperature T1. So we will get the mass flow rate of air to be 0.04709 kg per second. Okay, that's good. For compressible flow, we need to calculate the velocity at throat, and by this formula Ct, and we are given what values? We are given the values. Are we given the values of Pt? No, we are not given the value of Pt, rather we are given the value of P1 or Pa, and from this we are given the value of Ct, that is 85. We will calculate the value of pressure at the throat. So the value of pressure at the throat can be calculated in this manner, and we will get the value of 0.97 bar, that is the throat pressure. Then the volume flow of air at choke, that is by this isentropic process. Since it is an isentropic process, we will consider this thermodynamic relationship, and from here we will get Vt equals to, that is the volume of flow at the choke, is 0.04032 meter cube per second. So the finally the area of the throat is given by Vt divided by Ct into CdA equals to 0.04032 divided by 85 into 0.82, and finally we will get the area of the throat to be 578.5 millimeter square, and we will relate it to the diameter by this formula. And why this formula? Because now we have a emulsion tube, and we'll have to accommodate the emulsion tube, and for that we'll have to use the emulsion tube will come in the cross section of the jet delivering the fuel. So pi by 4 into d square by small d square is the area of the throat through which the fuel should move, and accordingly uh, since the diameter of the emulsion tube is 40% of the diameter of the main tube, so finally the choke diameter is 29.61 millimeter. The mass flow of fuel, mf equals to ma by 13, and finally we will get 0.003622 kg per second. So mf equals to cdf into aj, this formula we have calculated from Bernoulli's principle. So that is same for both the exact and the approximate analysis. And by this, if we put the values, we will only have the value of AJ left. So the mass flow of fuel will be AJ equal, sorry, the area of the through which the fuel should pass would be area of the jet will be 2.209 millimeter square. In terms of diameter of the jet, if we calculate, that will be 1.68 millimeter. So you see here, since an emulsion tube is placed, the air will have some restriction to flow, and it will have a restriction of the area through which it will flow, and that restriction is this diameter. Since it is concentric, and this is the diameter where the of the emulsion tube placed inside the carburetor uh, pipe, and accordingly there is a reduction in the total area. Then let us come to the next problem. So the problem now states the following data refer to a simple carburetor. So we are given the throat diameter, we are given the diameter of fuel orifice, we are given the coefficient of airflow, the coefficient of fuel flow, that is the coefficient of discharge, then level of petrol surface below the throat, density of air, density of fuel, and based on these values, we need to calculate the airflow ratio for a pressure drop of 0.065 bar when the nozzle lip is neglected, then the airflow ratio when the nozzle lip is taken into account, and the minimum velocity of air or critical air velocity required to start the fuel flow when nozzle lip is provided. So again, let us take 1 minute to understand this question and try to solve it. After 1 minute, I will solve it anyways. Okay, then let us try to solve it. So we are given this particular values. So the airflow ratio when the nozzle lip is neglected can be given by this. We have to find the airflow ratio. So first we calculate the airflow, that is mass of air is given by this formula we know. Now you will have to note that here we are not given the temperature at the inlet conditions. When the temperature at the inlet conditions is not provided, we need not follow the exact analysis, which is having a bigger formula that is quite monotonous, right? So instead, we can follow the easier approach, that is the appropriate approximate method. And by that, we will find the airflow, the equation of the mass flow rate of air is CdA into area of the air channel into square root of 2 rho A into delta PA. So are we given the value of delta PA? No, I think we are not given the value of delta PA. Oh, for pressure drop of 0.065 bar. So that part we are given. So we can directly place in the values. So fuel flow, the mass flow rate of fuel is given as the CDF into area of the fuel orifice, and into the square root of 2 rho f into delta PA. So the airflow ratio will be simple. Uh, the division of the both, and when we put in the values, we will get the airflow ratio to be 11.35. The airflow ratio when the nozzle lip is taken into account. So when nozzle lip is taken into account, the airflow will remain same. The fuel flow will become mass fluid of fuel, that is CDF into AF into root over 2 rho F into delta rho A minus GZ rho F. Accordingly, the airflow ratio will be this, because the mass fluid of the airflow will remain the same, right? Accordingly, we will have this value to be 11.39. So that is the answer for the second question. Then the minimum velocity of air C2. So the minimum velocity of air C2 is, for this we can follow this concept that the flow of fuel when the lip is provided will start only when the minimum velocity of air required to create the prerequisite pressure difference for flow of fuel to overcome the nozzle lip exists. So the minimum velocity of air will be required in order to create the pressure difference for flow, and for that will the pressure difference delta rho PA must be equal to the GZ rho F. Now that is the limiting condition, and we'll have to assume the velocity at the entrance of the venture to be C1 to be 0, and accordingly we use the Bernoulli's theorem in the sections 1 and 2. Then we'll get delta PA divided by rho A equals to C2 square by 2. Eventually, we will solve for the value of C2, and the C2 will be given as 8.58 meter per second. So that is the minimum velocity of air or critical air velocity required to start the fuel flow when the nozzle lip is provided. Okay. So this is the probably the last question. So the following data refer to an 8-cylinder 4-stroke petrol engine. So the data is given, the bore diameter is given, the stroke length is given, composition of the fuel is given. The C is 84%, H2 is 16%. Throat diameter of the choke tube is given. Volumetric efficiency at 300 rpm is 75%. Pressure depression given. The temperature at throat is given. Characteristic gas constant for air and for fuel vapor are given. If chemically correct air fuel ratio is supplied for combustion, we need to determine the fuel combustion consumption in kg per hour and the air velocity through the tube. So basically this is the setup, and these are the values which we are given, and we need to find the fuel consumption and the air velocity through the tube. So let us take a minute to understand this question and solve it. Okay, then let us try to solve this problem. So first, for the fuel consumption in kg per hour, so the volume of mixture supplied at 0 degree Celsius and 1 bar per minute we need to calculate. So that will be based on the bore diameter and the stroke length, and into the RPM, also the volumetric efficiency. And why 8? Because it's a 8 cylinder engine. And why n by 2? Because it's a 4 stroke engine, and for every 2 revolutions, one suction stroke is happening. So that's why we'll have to use n by 2. So if we substitute the values, we'll find 9.408 meter cube per minute. And also we'll do this particular this stoichiometric and this equation balance. So C plus O2 equals to CO2. Now again, 2H2O plus O2 equals to 2H2O, 2H2 plus O2 equals to water, 2H2O. And based on that, if we find the air required for combustion of 1 kg of fuel, we'll find that 0.84 times, that is 84% of carbon, 32 by 12. Why 32 by 12? Why? Because 32 divided by 12 plus 0.16 into 8, 16% into 8. So that is 8 of the oxygen atoms divided by 1. So 8 into 100 by 23, that is 15.23 kg, 15.3 kg for every 1 kg of fuel. So that is basically the air fuel ratio. So the air fuel ratio will be 15.3. Now we'll calculate the volume of 1 kg of air at 0 degrees Celsius and 1 bar. So we will use this thermodynamic relationship. Since 1 kg, this is MRT, so 1 RT divided by P, so that is 0.773 meter cube per kg. Similarly, volume of 1 kg of fuel vapor at 0 degrees Celsius and 1 bar, using the same formula, we will get the volume is 0.2614 meter cube per kg. Thus, MA per minute into VA and MA per minute into VF, that is 9.408, right? And based on that, if we calculate, we'll find the mass flow rate of fuel should be 9.408 divided by 15.3 VA plus VF. Substituting the values, we will get 0.778 kg per minute. So the fuel consumption is 0.778 into 60, that is 46.68 kg per hour. And the air velocity through the tube, for air velocity through the tube C2, we'll calculate first the density of air at the throat, rho A, equals to P2 by RA into T2. So P2 is the pressure at the throat, and P2 is given as P1 minus delta PA. Okay, and then substituting the values, we'll get rho A to be 1.08 kg per meter cube. Then velocity of the throat at the throat in meter per second, Ca equals to Ma divided by rho A by rho A. And finally, we will get the value of the velocity at the throat to be 132.59 meter per second. So this is a question. So this is supposed to be the last question. So we need to determine the air fuel ratio supplied at the 4500 meter altitude for 4.5 kilometer high by a carburetor which is adjusted to give an air fuel ratio of 14:1 at a sea level where air temperature is 25 degrees Celsius and pressure 1 bar, 1.013 bar. The temperature of air decreases with altitude as given by the expression T equals to Ts minus 0.0064 hours, where H is the height in meters and Ts is the sea level temperature in degrees Celsius. The pressure of air decreases with altitude as per relation. H equals to 19,300 log 10 of 1.013 divided by P, where P is expressed in bar at altitude. So this is a problem related to how in aircrafts the carburetor has to operate in order to supply the required airfoil ratio. So the performance of carburetor at such heights in aircrafts. So you just think about this problem for 1 minute and we'll again catch up. Okay, then let us solve this problem. So we are given this relation for temperature of air with altitude. Then at the altitude which we are given, we'll get the temperature of air to be minus 3.8 degrees Celsius. Then the H is also the we need to find the pressure also. Then we'll use this particular relation. We know the value of H, we do not know the value of P, pressure. So for P we will solve, and finally we will get the value of P to be 0.592 bar. So very low pressure, also below 0 degrees Celsius. So it's a very unusual condition for a carburetor at very high altitudes. So now the airfoil ratio at altitude divided by airfoil ratio at sea is given by rho altitude by rho sea level. Okay, so if you note, so the airfoil ratio at the altitude is 14 into P altitude divided by R T altitude. So we are replacing the density with pressure R and temperature. So based on that, we'll get this particular relationship. Substituting the values, we will get 11.26 is the airfoil ratio at that altitude that is required. Okay then, so that was for all the problems. Now we will get into the limitations of this carburetor arrangement. So this was the case for the simple carburetors, very simple carburetors without any augmentation, and there are certain limitations to it. So limitations of a simple carburetor is the first, although theoretically the airfoil ratio supplied to by a simple single jet carburetor should remain constant as the throttle goes on opening, actually it provides increasingly richer mixture as the throttle is open. So this is the because the reason that the density of air tends to decrease, the rate of flow increases. Aha. So that is a fault, and it is corrected by number of compensating devices, and we'll learn about that next. Then the second fault is during idling, however, the nearly closed throttle causes a reduction in the mass of air flowing through the venturi. So at such low rates of airflow, the pressure difference between the flow chamber and the fuel discharge nozzle becomes very small. It is not adequate enough to cause the fuel to flow through the jet. Then and this is augmented, means this limitation is solved by the fault is corrected by using an idling jet, which helps in running the engine during idling. And the third fault may be the carburetor does not have arrangement for providing rich mixture during starting and warm up. and for this, these kind of limitations are taken care by using a choke arrangement. So there are certain limitations, as we now know, and there are certain methods of correcting those faults, and now we will study about these kind of methods, uh, which are augmented to a simple carburetor in order to supply the desired air fuel ratio at the desired conditions. So a carburetor actually includes uh, the expected outcome from a complete carburetor is it should meet the demand of the engine under all conditions of operation, and for that additional devices or systems are added to the simple carburetor. The first is the main metering system. So in order to operate for a load of 25% to 75%, the main metering system is used. So this is where the range of operation is happening. Then for idling system, that is used when the car is operating at a very low speed, or when it is stopped. Then power enrichment or economizer system, so that is used in this range above 75% of load, and for that a high rich mixture of air fuel ratio is needed, and that is supplied by this system. Acceleration pump system, that is also when suddenly accelerator is given and we need to sudden acceleration is a transient phenomena, and for that sudden requirement of high rich mixture of fuel, this charge is required, and to supply that we need a acceleration pump system. And finally the choke, so the choke is used to generally operate at to warm up or when cold startup. So in that case generally uh, a choke is used, and we will see how it operates. So first, the main metering system. So for a main metering system, again, uh, so main metering system of a carburetor, it should be so designed as to supply a nearly constant fuel air ratio over a wide range of period, that is operation, that is from 25% to 75% load. This fuel air ratio is approximately equal to 0.064 AF ratio, almost 15.6, for best economy at full throttle. In order to correct the tendency of simple carburetor to give progressively richer mixtures with load speed, the following automatic compensating devices are incorporated in the main metering system. The so these are the these devices are augmented to the this carburetor, and all of the devices when operating together consist of the main metering system, and we will see how all of this works one by one. So first is the compensating jet device. So here you can see the for compensating jet device, what actually it means is that sometimes uh, in addition to the main jet, a compensating jet is provided in which a communication with a compensating well. The what happens is that as the air flow increases, the level of fuel in the compensating well decreases, thus the reducing fuel supply to the compensating jet. So when compensating jet, as the word means, it is used to supply extra amount of fuel, and extra amount of fuel when it is required. So actually the main jet and the compensating jet are reverse of each other. If a large amount of fuel is supplied from the main jet, the compensating well will not supply enough this fuel, and such in that condition, what happens is that uh, it will make uh, the compensating jet will make a leaner mixture, main jet will make a richer mixture. The combination of both will have a finally it will maintain the required stoichiometric ratio of the mixture. So what happens is that this is a compensating well in which the oil is poured, and due to the atmospheric and the flow chamber is connected to this compensating well through this orifice, and this orifice is quite small. And when the engine is operating, um, in this engine is operating such that for a long time the throttle valve opens, uh, uh, means for a higher combined jet mixture is required. So in that case, what happens is that the well, the flow from the well actually depletes the flow liquid in the well, and the orifice is not able to supply the same amount to retain the entire volume of the compensating well. In that case, after a certain time, the compensating jet will not be able to supply fuel into this channel, but the main jet is able to supply the fuel, right? And accordingly, you will have a linear mixture. So at a long range, uh, higher amount of to reduce the fuel loss, this application is quite suitable. So what it does is that the compensating jet thus progressively makes the linear mixture as main jet progressively makes the richer mixture, and the sum of the two remaining constant. You see, the compensating jet, the fuel air ratio, it decreases. It subsequently makes a very low mixture, and here the main jet, the fuel air ratio, it increases, and the sum of both becomes constant as a combined jet. So the main jet and the compensating curves are more or less reciprocals of each other. So that we can see right now, right? So that is for the compensating jet device. Next is emulsion tube or air bleeding device. So a mixture correction in the modern carburetor is done by air bleeding alone. What happens? A main metering jet is fitted 25 below the petrol level in float chamber, and therefore it is called the submerged jet. So here it is submerged jet below 25 This main jet is submerged. The jet is situated at the bottom of a well, and the sides which have holes which are in communication with the atmosphere. And these are in since it is communication with the atmosphere, so it is in atmospheric pressure. Then air is drawn through the holes, and the atmosphere is emulsified. All right. So the pressure difference across the petrol column is not as great as that of the simple carburetor, and what impact does it give is that initially the level of petrol in the float chamber as and the well is same, but eventually when the throttle is opened, the pressure at the venturi decreases, it decreases, and the petrol is drawn into the airstream, right? And this is progressively uncovering the holes in the central tube, leading to decreasing fuel air ratio or decreasing richness of the mixture. So since the air is bleeded through the holes, the air content is high, so the fuel air ratio is decreasing, and hence the richness of the mixture is also decreasing. Normal flow then takes place from the main jet. Right. So that is the emulsion tube or air bleeding device. Next is the back suction control or pressure reduction method. So here you see this is the arrangement for the back suction control or pressure reduction. What happens is that it is commonly used to change the airflow ratio in large carburetors. So if suppose airflow mixture is required to change, and for that in large carburetors it is generally inconvenient to suddenly change the airflow ratio. So in that kind of cases, the device arrangement includes a venting. A large vent is connected from the fuel float chamber to the air inlet, and a small vent is connected through the orifice to the throat of the venturi, as you can see here. Now, what happens is that there is a control valve which is connecting the air to this level. So when the valve, this control valve is wide open, so this point is connected to this point. Hence, if the pressure here is P1, then the pressure out here is also P1. And in the venturi, the pressure is low, that is reduced to P2, right? So then what happens is that the pressure difference is created, P1 minus P2. That is not sufficient to cause uh, uh, so what happens is that the pressure differential acting along the orifice is P1 minus P2 when P2 is this. So when the valve is closed, the flow chamber communicates only with the venturi throat. Now, due to this pressure difference P1 minus P2, the fuel actually will continue to move from the flow chamber through the orifice into the venturi. And when the control valve is closed, this section will not be connected to the flow chamber. And accordingly, what happens? The P1, this here the pressure will not be equal to P1 because it is not connected anymore. And now the pressure in here will be equal to the pressure out here. And when that causes, the fuel will not move to this location. Why will it move? Because the pressure differential is now 0. The carburetor depression will be now 0 for the fuel to move. And in that case, no fuel will be supplied and it will be resulting in a very lean mixture. So by proper adjustment of the control valve, any pressures between P1 and P2 can be obtained in the flow chamber, thus altering the quantity of fuel discharged by the nozzle. So that is the whole concept. Next, we have the auxiliary valve carburetor. So the concept is we have an auxiliary valve out here which can supply air out here, and we have the normal carburetor system with the nozzle out here in the venturi throat and air supplied through this, and this is the throttle valve. So when load on the engine increases, load on the engine, it increases, the vacuum and the venturi throat also increases, right? The venturi, if the venturi throat, the vacuum increases, what happens is that this will also cause a large pressure differential between the float and the nozzle, and accordingly large amount of fuel will be supplied to the venturi throat, and that will a richer mixture will be created, and we do not want that. So we want the mixture to be remaining lean, and for that we require larger amount of air. So the remaining amount of air is supplied through this auxiliary valve. So what happens, the pressure differential or the throat pressure is now quite less. That actually opens this spring loaded auxiliary valve, and the air is allowed to enter into the carburetor channel, and accordingly what happens is that a leaner mixture is formed, and that linear mixture is supplied to the engine cylinder. So consequently, more air is admitted and the mixture is prevented from becoming overrich. So that is the whole concept between auxiliary valve carburetor. So these are the systems in main metering system. So the next is the auxiliary port carburetor. So uh, what happens is that at very high altitudes, for carburetors that are operated that are supplying the fuel for aircrafts engines, generally the density of air is very less, and for that the mass of air that is moving into those engine cylinders are quite less because of the density, and that mass should be corrected, otherwise the mixtures will remain very rich. Okay, so in order to maintain that, we'll have to supply extra amount of air without mixing it, because the density of air is less. In order to make the mass constant, we'll have to supply a higher volume of air, and the volume flow rate of air should be increased. In that case, what happens is that auxiliary port is given, and the port is controlled by a butterfly valve. So the butterfly valve, when it opens, it admits higher amount of air through this channel, and the normal amount of air is being supplied through this. So the normal amount of air is actually creating a richer mixture. When this amount of air mixes with this normal rich mixture, the mixture becomes lean, it becomes in operating conditions, and finally this normal mixture compared to a richer mixture is supplied to the engine cylinder. So that is the entire case of an auxiliary port carburetor. So we have now understand how the main metering system works. The main metering system The objective of it is to operate the engine cylinder or supply the uh, air fuel mixture to the engine cylinder at load conditions around 25% to 75%, which is also called as the cruising load. Now we will understand what is required extra if we need to operate it at a very low speed or idle condition. So earlier as discussed, at idling or low load condition requires a rich mixture. So we have already discussed, because the pressure differential between the engine cylinder and the exhaust valve is not high, so the dilution of the charge happens when the unburned gases are not completely removed from the cylinder. It mixes with the fresh charge that is coming, and that actually reduces the efficiency if the fuel is not supplied at the higher amount. Since the fuel needs to be supplied at higher amount, a rich fuel air mixture is needed to be supplied. So the main metering system, it fails to supply the enrich the mixture at low air flows, but also cannot supply any fuel during the idling operation, right? At low condition it cannot supply. So that's why this entire idling condition is uh, uh, means made. So what happens is that there is a uh, in the float chamber, a connection is made, that is the idle jet, and that is a air bleed is also made, and that connects to the downstream of the throttle valve. So what happens, the air comes in, and at the downstream, almost at the downstream, when the throttle valve is almost closed, still it can supply the air at the downstream, air and fuel mixture. So that is the idle system. And how it works is that there is a idle adjust. Through the idle adjust, we can ensure the amount of air that needs to be bleed uh, to the through the channel. So the air will bleed, it will take away the fuel through here due to the pressure differential, and this entire air fuel ratio will this charge will go inside. And also here there is the normal system also running. So here the fuel will be supplied. Here the fuel will be supplied, the extra fuel will be supplied through this idle jet, and accordingly uh, the rich mixture condition is satisfied. So this is an ideal system, and that is used at low speed or idle conditions. Next is the power enrichment or economizer system. So power enrichment or economizer system. So what happens is, when maximum power range and the car or the vehicle is operated at maximum power range, then that is around 75% to 100% load, a device should be available to allow richer mixture fuel air ratio about 0.08 to be supplied despite the compensating leanness. So so this is the arrangement that is given for a power enrichment economizer system. So what happens is that as the load increases, so high amount of air will flow. The depression around is here is high, because the throttle is now almost completely open, right? We need higher amount of fuel air mixture. So when it is completely open, it will actually push this arm open in here in this direction, and it will uh, move this lever above. So this lever is connected to an orifice which actually supplies the fuel to the venturi, and accordingly when this orifice opens, then a higher amount of fuel will be supplied, and accordingly it regulates the additional fuel supply for above operation or higher percentage load. So the term economizer is rather misleading. It stems from the fact that such device provides a rich, uneconomical mixture at high load demand without interfering with the economical operation in the normal power range. So that is the whole motivation, and that's why this setup is made or augmented to a simple carburetor. So that is power enrichment or economizer system. Next, we have the acceleration pump system. So acceleration means suddenly we need to increase the car speed or torque. So sudden acceleration is required. So these kind of conditions are not steady state, because these are transient. Suddenly we require this kind of condition. So acceleration is a transient phenomena. In order to accelerate the engine rapidly, a very rich mixture is required, which a simple carburetor may not be able to supply, right? So in order to quickly supply a rich mixture or quickly supply a higher amount of fuel, this kind of system is augmented to a simple carburetor. So what happens is that there is a pump, there is a plunger, and when the plunger moves through the pump, so what happens, a higher amount of fuel is released from the float. And also there are certain holes in here. So when the pump moves in very slowly, then the oil leaks out and goes into the float chamber, so there is no purpose of it. When there is a sudden motion of the plunger into the pump cylinder, then the oil does not get enough time to leak out, and eventually this oil will move into the this channel. So what happens is that when the throttle is suddenly open, so it senses the sudden operation of the throttle and sudden increase operation, and accordingly what happens, the this lever, it is pushed down, and accordingly this plunger is pushed down. And if the motion is sudden, then this plunger will have a very high velocity when it is entering into the pump cylinder, and accordingly a high amount of fuel will be supplied to the carburetor channel. But when the plunger is when there is a very small rate of throttle position change, the throttle is changing, throttle is opening very slowly, then this motion will have very slow velocity, very low velocity, and accordingly the plunger will have very low velocity when it is entering into the cylinder of the pump, and during that all the oil which it needs to pump out, it will be leaked out and will come into the flow chamber. Accordingly, this rich mixture of fuel, air mixture, will not be provided. So it senses in based on that way, and that is the acceleration pump system when we need to suddenly accelerate our vehicle. Next is the last system, that is a choke. So choke is basically a butterfly valve which is present at the yeah, entry of the whole carburetor, through which the air enters, and the purposes may be such as starting of a vehicle which is kept stationary for a long time, maybe overnight, during cold winter seasons, is often very more difficult. So at low cranking speeds and intake temperatures, a very rich mixture is required to initiate the combustion. So a very rich mixture is required. Some sometimes as high as 5 to 10 times more fuel than usual mixtures is required. The main reason is that large fraction of fuel may remain liquid suspended in the air, even in the cylinder, and only the vapor fraction can provide a combustible mixture of air, right? The more popular method of providing such mixture is use of choke. A choke is simply a butterfly valve located between the entrance to carburetor and the venturi throat, as shown in figure out here. So when a choke is partly closed, large pressure drop occurs at the venturi throat, would normally result from amount of air passing through the venturi throat. Yeah. The very large carburetor depression at the throat inducts large amount of fuel from the main nozzle and provides a very rich mixture, so that the ratio of the evaporated fuel to air in the cylinder is within the combustible limits. Sometimes the choke valves are made with spring-loaded bypass to ensure that large carburetor depression excessive choking does not persist till the engine has started and reached a desired speed. The choke can be made to operate automatically by means of a thermostat, so that choke is closed when the engine is cold and goes out of operation when the engine warms up after starting. So that is the purpose of the choke, and we usually use it when we are starting maybe a scooty or bike after it is in cold winter seasons, when it is kept for a very long time idle or not operative. So we required a choke. You may remember pulling a particular uh, needle which is below the handle, and that is basically the choke. So this is the purpose of the choke, and this is the arrangement, and accordingly, accordingly, so the richer airfoil mixture is supplied. So that was the all the systems which are augmented to a simple carburetor in order to increase its productivity, in order to have a desired airfoil mixture at various conditions. And this was the so we have learned how to solve the questions related to a simple carburetor, and we now have learned how to make the carburetor more productive by augmenting different kind of devices. So that was the entire um, motive of this session. And uh, so here let us conclude. So thank you and hope to see you in the next session. Okay then. Bye.